Hi everyone, thank you for joining us for today's webinar, how to set up your INS for drone surveying. I'm Jeff Bestbroad, Marketing Executive here at OxTS, and presenting the webinar today is Sam Suleiman, Senior Support Engineer. Sam will be talking about some of the best practices for configuring an OxTS INS for LiDAR surveying using drones. The session will cover several key topics, including the correct initialization and warm-up procedure for OxTS units mounted on drones, the importance of vibration level settings, the use of GNSS recovery and GNSS weighting options, the use of SBAS, NTRIP, field base station, and RINEX corrections, amongst a few other topics. The presentation is due to last approximately 30 minutes, and there will be some time for questions and answers at the end. If you would like to ask any questions during the presentation, you can ask these using the drop-down menu, which is located at the bottom of the panel on the right-hand side of your screen. If you do ask any questions here, we will answer them at the end of the presentation. And the webinar will also be recorded and a copy sent out to everybody who registered tomorrow. So without further ado, I'll hand you over to Sam.
Thanks, Jeff. Thanks, Jeff, and welcome everyone. We swap moderators too often. Apologies. Okay, so welcome everyone. The focus of this is going to be obviously surveying with drones, so the settings that you need to implement in order to have the best possible outcome out of your INS. We'll be looking very shortly at the role of the INS in all of this, what you expect from it, the issues that can prevent you from getting an optimal output, and the advanced settings that will allow you to ensure you get that output. So very quickly, the INS obviously is responsible for providing the parameters that will allow you to georeference your data, be it, say, LiDAR scans or photo camera or other sensors data. First of all, time, obviously, to synchronize all the data, and then position, either in terms of absolute, lat, lon, and alt, or in a local coordinate system, perhaps, orientation angles, heading, pitch, and roll of all the survey instruments that you will have. And in addition to providing this data, obviously, the integrity of the data is also an important thing. So you need reliable time, position, and orientation throughout your data collection. All of this is demanded of the INS. So what can prevent you from having an optimal output? One of these four things mainly. A wrong or less than ideal physical setup, or a wrong or less than ideal configuration of the unit, an incorrect initialization, and incorrect or insufficient warm-up of the INS. So we will go through the correct ways of doing all of this, plus at the end, I will add some information that you can hopefully find useful. Okay, the physical setup to start with. First thing, one of the main sources of the data that the INS provides is obviously GNSS data, so the antennas. These need to be properly mounted, as in protected from multipath. So from anything that can interfere with the quality of the GNSS data. And the first thing is to guarantee that you have suitable ground planes. So some metal surface large enough, say a diameter of at least 10 centimeters, but then it will depend on how large your antenna is. On drones, that won't be too large typically. A metal surface underneath the antenna to protect it from multipath, at least from below. The other thing is thinking of EMI that you can have on your drone. A LiDAR, for example, can be a source of EMI, a camera, cables. Ideally, you should try to put any source of EMI, if you can, or about, we say, as a rule of thumb, about 1 meter away from the antenna. Obviously, we appreciate that on drones, this is not always possible. You might not have that luxury if your drone is not, big, to have 1 meter. But it is always good to put some thinking in the way you position things on the LiDAR, on the drone, so that you keep some distance from the antennas. And if you cannot guarantee that both antennas are at safe distance from any EMI source, at the very least try to protect the primary antenna as much as you can, because it's more important than the secondary antenna. Cables also think of the way you route them, and again try to take them away from the antennas. Depending on the LiDAR model and everything, you might get away with a shorter distance than that. Every specific model will have its own strength of EMI. So depending on that, you will need, say, a larger or a shorter distance. 1 meter is a rule of thumb. I've seen cases where it can perfectly work even with half a meter. Okay, another issue that is frequent on drones is mechanical vibrations. So we will see later on in a bit that you can configure the system to handle high vibration levels, but it's still very important that you try to damp those vibrations down as much as possible mechanically, so through proper mounts. And then whatever vibrations are left, you can configure the system to deal with, but try to limit as much as possible the level of vibrations that the drone can suffer while it's flying. And that is typically done through proper vibration mounts. Another important thing is that since the INS has to georeference the LiDAR data, they have to move in unison. So they need to be mounted rigidly together. Absolutely no play whatsoever between INS and LiDAR, or INS and camera, or whatever sensor you are using. No play. Whatever motion the sensor has, the INS does the same exactly. An aspect that is at times overlooked is the arms, the structures that hold the antennas need to be strong enough so that they do not vibrate too much during the flight. And when I say too much, I mean in such a way that the position of the antenna changes significantly from the starting point. Take care doing that. Make sure that the antennas do not move too much during the flight. Obviously, they will vibrate if the rest of the body of the drone is vibrating, but they shouldn't change too much their location, and that is achieved by having a rigid enough, a strong enough arm that is holding the antenna, that is appropriate for whatever weight the antenna has. Okay, that's for the physical setting. So quick things really. Now we move to the configuration. We have a lot more things to discuss here. So first of all, just a quick one. When you open navconfig in the first page that you see, you have an option of selecting what sort of application you will be using, and it would be good to select the appropriate one. So for example, in the case of a drone, that would be rotary wing. This will not implement any special configuration on your system, but what it will do, it will customize navconfig, so you are only presented with the options that are relevant to you, and you will not be presented with other options that, for example, are only applicable to a land vehicle. So you need not to waste time during that. Okay, to configure the INS, first thing to look at are the lever arms, so the distances along the 3 axes between the IMU and the primary antenna. This needs to be very accurate as you can. Now, the best way of doing this is to measure that as good as you can, say within 1, 2, 3 centimeters, if you can measure that. Leave the tolerance, the default tolerance on the measurements at 10 centimeters. Okay, even if you are confident your accuracy is better than 10 centimeters, but leave the tolerance, so the uncertainty, if you wish, on that measurement at 10 centimeter, which is the default, and then run a calibration run. We will go through this in a minute. In this way, the system will be able to automatically measure the exact lever arms, the exact distance between the antenna, the primary antenna, and the IMU. An important thing is that the calibration run needs to be done in RTK or PPK. So either you are having corrections in real time, or you can post-process the data, applying corrections such as Linux files in post-processing. Okay, it has to be, you know, an RTK or PPK level of accuracy if you wanted to get that spot on. And once you have done that, you can use the improved configuration tool included in navconfig to upload the improved configuration. Alternatively, if you don't want to do a warm-up and you want to figure it out yourself, you know, because for example, you know, you can measure it very accurately, or you have CAD models, then you can measure it yourself as accurately as you can, and then the advice is to tighten the tolerances manually down to 1 or 2 centimeters, depending on how confident you are. Tightening the tolerances basically reduces the uncertainty that the system will have to cope with. It's different if you tell the system that the antenna is, you know, in a given location relative to the IMU, plus minus 10 or 20 centimeters, or if you tell it that it's plus minus 1 or 2 centimeters. You are reducing the level of uncertainty, and that helps the system achieving a tight accuracy quicker. The important thing to remember is that setting a tight tolerance on a wrong measurement is worse than leaving a loose tolerance. Okay, so do not tighten the tolerance beyond reason, say beyond what is reasonable to do, because there is no benefit in doing that if the measurement is, you know, not that accurate. A couple of things that you will have to measure manually and that the system will not improve for you, not on a drone. So one is the 3D distance between primary and secondary antenna. Okay, the system will not refine this. You will have to measure it yourself, and again, do that as accurately as possible and tighten the tolerance down to 1 or 2 centimeters. That is the level of accuracy that you need to measure that distance to. The other thing is the orientation angles between INS and the frame of the drone. Now, this is relevant depending on basically how you collect your data. If you have your sensors in the IMU frame, then basically the way that the INS is aligned with the body of the drone is not that important, because eventually you will bring everything down to the IMU frame, so to the INS frame. But if you were referring to the drone frame, so to say, so you know you have a point on the drone from which you are measuring everything, then you want the INS to be aligned as accurately as possible with the drone itself, with the body of the drone. So try to do that, mount it in a way that it's easy basically to align it, and again, set the tolerance on the IMU orientation to 1 or 2 degrees if you can achieve that level of alignment between the INS and the body of the drone. So in navconfig, this is the button that allows you to launch the improved configuration tool. This is an example of an improved configuration, an automatically improved configuration. So as you see, unlike a land vehicle where the system will figure out this and calculate the exact relative orientation between IMU and the body of the vehicle, on a drone, this is not possible. So you need to do it automatically because you have fewer reference points than what you would have on a land vehicle. But what it can do is definitely tighten and calculate accurately the primary antenna position in the IMU frame and correct it, and also bring the tolerance down, or the accuracy, from 20 centimeters, for example, down to 1. And also it will correct the orientation, the relative orientation and height offset between the secondary and primary antenna. Not the distance between secondary and primary, but the relative orientation and height offset. In navconfig advanced tools accuracies tab is where you can manually tighten the accuracies on your measurements. In this case, we have them very tight, 0.5 degree on orientation and 1 centimeter on lever arms. If you can do that, that's better. Like I say, the more you tighten the tolerances, the less uncertainty the system have to cope with. One aspect that is not part of the configuration of the INS, but it's still very important, is the bore sight alignment between INS and LiDAR. So just a quick note on this, angles between INS and LiDAR have to be known very accurately, because that will impact the level of accuracy that you achieve on your point cloud. Any misalignment will show up in the point cloud. It's worth mentioning that we have a software georeferencer that can provide you an automatic tool to figure out this bore site calibration and do it for you, data-driven bore site calibration. So you can calculate the angles between LiDAR and INS very accurately. Okay, back to mechanical vibrations. As I mentioned, try your best to dampen them down at the installation level, but then you can also configure the system, to cope with a higher level of vibrations. So one of the things that we rely on to do that is the assumption that you are using the LiDAR and the drone in a good GNSS condition. Okay, assuming the drone is flying over things, so you do not have a lot of objects that can obstruct the GNSS signal. And again, this is an assumption. You might be in a situation where, say, the drone is flying in between tall buildings, so the GNSS reception is not that good. But that is a further complication, and if you are in that situation, then you can get in touch with us and we can try to sort out the best way of doing this. But generally speaking, a drone would be flying over things, so we start from the assumptions that you have a good GNSS reception. So what we do is basically setting more trust, more weight on the GNSS data and less trust on the IMU data. The way to do this, and I'll show you in a minute where you can do that, is to set the GNSS recovery to value of 2. So basically what we are saying, just wait for 2 updates. The default is 20, to give you an idea. If the IMU data and the GNSS data disagree, who should I trust? So by default, the system will wait for 20 GNSS updates before it believes the GNSS over the IMU. You shift this to 2. So basically what the system does is immediately believing the GNSS over the IMU. Why? Because the level of vibrations you have set to high. So instructing the system that the IMU data will suffer from vibrations. And if you have huge vibrations, and I do not recommend you get in that situation, but if you do, you can also set it to very high. So you limit the trust in the IMU data significantly. Obviously, this comes at the price that the system will struggle a bit more in achieving a perfect accuracy. So the best way is to dampen down the vibrations mechanically. And again, if you have some vibrations left, you can cope with, ideally through setting the system to high and not having to resort to very high. Okay, so in the environment section in navconfig, you set the vibrations level to high. And as you see here, the GNSS environment is open skies. Again, we are working on that assumption. And in the advanced tools, GNSS recovery tab is where you can set the position updates that are required before the system believes the GNSS over the IMU to simply 2. So it is very quick in believing the GNSS data. Examples. On the left, you have the original data that was collected with improper vibration settings. And what happened here is that the vibrations messed up the initialization of the system. We will see initialization in a minute. By simply modifying the configuration in post-processing, applying the 2 changes that I've just described, so setting vibrations to high and GNSS recovery to 2, you have your trajectory, nice and accurate back. This red line here on the right is what really happened. As you see, by post-processing the data, by applying the correct configuration, you can get your data back, even if in real time you had a bad result. Okay, initialization. So initialization is basically the moment when the system figures out its own directions. It knows which way is up, which way is forward. This is what we mean with initializing. We have 2 ways of initializing on our systems, a dynamic and a static. The dynamic requires motion. Problem is, it is important if you initialize dynamically to move straight and forward. So you are telling the system that the direction that it is moving in, that is forward. And on a drone, that might be difficult because you might have crosswind that is pushing you slightly sideways. So what is forward isn't really, and you get the directions wrong. So where possible, I would recommend using static initialization instead, based on the relative position of two antennas. So you don't need motion, you just leave the system stationary until it initializes. And if your configuration is correct, static initialization can be very quick, down under a minute. So it doesn't take too long, assuming two things: one, the configuration is correct, and the other thing is static initialization requires good GNSS data. Because you are not moving, all you have is GNSS data, right? You cannot use the IMU data in that instance because there is no motion, no relevant input to the IMU. So all you have is GNSS data, so it needs to be good. So pick a spot that is open sky with a good visibility of the sky. And second thing, avoid gathering around the drone because the human body is, an obstruction to GNSS signal. So if you gather and group around the drone, you will get in the way of the GNSS signal. So just stand a bit back, leave the system to initialize. If you use dynamic initialization, one thing to be aware of is to set the speed threshold. So basically the system initializes dynamically when it reaches a given speed. That is the speed threshold. So if that is not high enough, what can happen is that you initialize accidentally. So imagine you are moving, flying the drone very slowly because you want to get it in the starting position, so to say, from which you launch it into initializing, making sure it moves straight and forward. But in order to do that, you will have to move it at some speed. So if your speed threshold is very low, what can happen is that the system will initialize before you intended to, if that makes sense. So you avoid this by setting a threshold that is high enough so that you can make sure that you won't hit that speed until you really want to, and you push the drone to reach that speed. 5 meters per second is the default, and it's usually enough. Final thing, both for dynamic and static initialization, try to choose a level spot if you can, and to fly the drone flat. But if you cannot pick you are on a slope, say, and you are initializing statically, just configure the system to be not level. So tell the system that it is not, on a level, so it can get its directions and orientation right. Okay. This is where you set both, you enable static initialization if you wanted, and also you set the threshold in the environment section in navconfig. On the left, an example of a wrong initialization. In this case, a wrong dynamic initialization where the system wasn't really flying straight and forward when it happened. And on the left, switching, you can sort it out in two ways. Either you switch to static initialization if the GNSS data is good, or you pick a point where the system was actually like here or here, or here. You pick a spot where the system was actually traveling straight, and in post-processing, you force the system to initialize at that point. So it initializes correctly, and again, in post-processing, you get your data back. Okay, warm up. So the warm up is basically getting the unit ready to perform, so to say. And on our systems, you have a window of 15 minutes, but it doesn't take 15 minutes. Okay, you have two types of warm up. One is the calibration run that I have described earlier, and that can take a bit longer, but you only do that once. The other is the warm up that you do right before collecting the data, and that can be very quick. Like, for example, on our new XNAV 650 is under 5 minutes, can be as short as 2 or 3 minutes. If you are starting from an already improved configuration, like I described earlier, it can be under 2 minutes in real time. And if you are using combined processing in post-processing, it can be even shorter, even under a minute. Okay, so during the warm-up, choose an open sky spot and give it a varied motion so that you excite the sensors as much as possible, and the system learns, how to put the IMU and GNSS data together. If you are doing a calibration run, the one that we discussed earlier when we discussed how to improve your configuration, that is worth doing a bit longer, like say 5 to 10 minutes. But you only need to do that once. If you do not change your configuration, right, and your antennas and your IMU are mounted in the exact same spot every time, so you don't have to reconfigure the system. You do it once, you save that improved configuration, and you can use it all the time. Okay, no need to redo a calibration run every time. What you need to do every time is just a short warm-up at the beginning with some varied motion and in a good GNSS environment. So when we say varied motion, figures of 8, straight lines, sharp turns left and right, and variation of altitude, all of which you can easily do with a drone. Generally, if you know that you will be doing a specific kind of motion during your survey, include a short portion of that in your warm-up, so that the system is prepared to cope with the type of motion it will have to handle in real time. So if you are doing a calibration run, again, do a few of each of these so that it takes between 5 and 10 minutes overall. If you are doing a shorter warm-up, the one just before starting data collection, a couple. So it really shouldn't take you more than 2, maybe 3 minutes. No more than that, really, a couple of minutes. Okay, finally, just a few information that hopefully you can find useful. A word on datums and altitude reference. So there are obviously, as you know, different datums that you can have your data in, your position data in. And our system allows you to choose between a set of the main ones. So WGS84, NAD83, ETRS89, and so on. Also, the altitude reference, you can choose 3 things really: ellipsoidal, geoidal, and that will be based on whatever model the GNSS receiver has. So it depends on what kind of unit you have, because we have different GNSS receivers for different units. We use Novatel, we use U-Blocks, we use Topcon. It depends on what specific unit you are using. Also, you can customize the geoidal undulation. So if you are in an area and say the correct undulation for that area better than the receiver does, say, you can customize that and introduce an undulation in your configuration. This is where you do it in the Advanced Tools Global Coordinate System. You select the datum for your output and you select the altitude reference. And as you see, you have the customizable offset option. So you can go geoid custom. The output displacement, this is also sometimes a useful thing. So instead of having the output, your position and all of it, for where the IMU, for where the INS is mounted, you can choose a different spot. For example, the place where you have mounted the LiDAR or the camera. So instead of having the output, again, where the INS is, you have those values for your sensor. And you can do that in post-processing as well, not just in real time. So you can post-process your data, for example, several times and move the output point around if that is what you need to do, instead of doing the math yourself, say, and project the IMU data on a different point, because that is what you need to do. The system can do that automatically for you through the output displacement tool. Not strictly required. For example, our georeference software will calculate the displacement between INS and LiDAR. It will do that automatically. This is where you do displaced output. Again, advanced tools, displaced output, and just what you need to do is just put in the lever arms between INS and the point that you want to use as an output. A quick word on differential corrections. There are different types. Oh, excuse me. Different types of this. So SBAS to start with, which is a free one, but keep in mind that it's only compatible with GPS satellites. So if you have other constellations enabled, like it's typical on our systems, now the XNAV 650 is quad constellations, the RT3000 is quad constellations. So you can have, Galileo, GLONASS, Beidou, in addition to GPS satellites. SBAS is only applicable to GPS. So if you are using those corrections, you are basically, not using the other constellations. So you need to evaluate whether it's worth having a more accurate, and not terribly accurate. I mean, SBAS gives you an accuracy of about 35-40 centimeters. So not a huge improvement over SPS, which is the standard mode that can get you down to 50-60 centimeters, sometimes even better. But sometimes you want to use that. Remember that it's only applicable to GPS satellites. Other ways of getting corrections, obviously using a field-based station. You need a radio link between the base station and the system, and obviously it cannot be applicable to a very extended area, or if you have obstacles in the way that prevent you from having a clear line of sight. N-trip corrections is a good option. It can cover wider areas, but you will need a good mobile internet connection on your system to get that N-trip stream in real time. A lot of times you do not need corrections in real time. If you are happy to post-process your data, then you can also improve the accuracy of the INS data in post-processing by applying RINEX files, for example. And obviously they have the advantage that there are no interruptions in the RINEX stream. Unlike N-trip, for example, or real-time corrections, you can be assured that you won't have interruptions in your stream. The downside can be that you will have to need a base station that is close to you. And obviously you will have to check if that's the case. But a way around it, for example, is to use one of our field-based stations that you have to place in some vicinity of the area that you are intending to survey in a good GNSS area, so that the base station can log good GNSS data. And instead of having corrections in real time sent from the base station, which, as we said, can be difficult, you can leave it to log GNSS data and then download RINEX files from it. So basically, you put together the positive aspects of both things. You leave the base station to log data, so you can take it with you wherever you go, and then you download the RINEX files, and then you can apply them in post-processing. That's a way of doing things. For example, if you are in an area where you don't have, say, providers of corrections. And a final thing is, keep in mind the datum of differential corrections. They always come with a datum attached. You can specify that in our software, but you need to know what the datum is. So this is where you select the corrections type in the hardware setup page. So you can select, say, RTCMV3, enable N-trip if you wanted, enable SBAS if you wanted, and so on. And finally, a word on post-processing. We've already seen how correcting the configuration in post-processing can get your data back, basically. So even if you had bad results in real time, by tweaking the configuration in post-processing, you get sensible data. Also, you can add differential corrections, as we mentioned, and also there is a tool that is called the combined processing tool, the forwards and backwards processing, that is very powerful in improving the quality of the data, the accuracy of both position and orientation. The way it works is basically, instead of just processing forwards, so same as in real time, say, it processes also backwards in the opposite direction, and it puts together the best data that it gets from both traces. This helps especially in cases of a non-ideal GNSS data. It can limit the spells where you have bad GNSS data and a bad position accuracy because of that. If you know that you are going to process in combined mode, what I would advise is to include a very short warm-up, like a minute, after you have ended your data collection. So not just at the beginning, as we discussed, but also at the end, because that is what the backwards trace will see at the beginning and use it as a warm-up, if that makes sense, because you are going in the opposite direction. Whatever is at the end is what the backwards will see first. So that will help warming up the backwards trace, so it's of good quality, and it can be used along with the forwards one to give you the best result. So in practice, if you are initializing statically, just leave the drone stationary for about 1 minute at the beginning and at the end, at the very end, and do 1 minute of straight lines and figures of 8 at the start and at the end. So the sequence would be you initialize, you do a short warm up, then you collect your data, then you do another short warm up or a warm down if you wish, and then you de-initialize, because the backwards also will need to initialize in the same way as the forwards does, except it does it at the end. Okay, just to give you an example, couple of comparison between combined and simulated. The blue line is simulated, the combined is the red one. In terms of position accuracy, you can see that where you have above 1 centimeter, say, and with some peaks up to 3 centimeters with the simulated, just processing that to combined, it gives you a solid below 1 centimeter accuracy, between half centimeter and 1. So, a visible improvement. And also on orientation, this is pitch and roll that you are seeing here accuracy. So you move from 0.1 down to, say, maybe 0.8, 0.7 in simulated. You have a solid 0.1 to 0.07 degrees of accuracy in simulated mode, down to 0.03, 0.04 in combined mode. Okay, so you improve both your position accuracy and your orientation accuracy just by processing combined. Okay, thank you.
Thanks, Sam. Really great presentation there, as always. We have a few minutes left before our time runs out. So if anybody has any questions, please feel free to ask them now. We don't have any questions coming in just yet, Sam. I think you've covered all of your points brilliantly.
Yeah, thanks. Well, obviously, if should you need to learn more, say, about our systems, a good place to go is our, say, support help center, where we have plenty of articles and guides. So any, say, specific argument or topic you are interested in, you are likely to find something on that. And also, if you have technical issues or technical questions, the best thing to do is to send an email to support@oxts.com, the email address that you see, on your screen, and we will get you an answer within 1 working day. Okay, thank you.
Yeah, thanks, Sam. Still no questions in, but like Sam mentioned, if anybody thinks of anything after the event, then yeah, please feel free to let us know. Yeah, still no questions, Sam. So yeah, probably best to end it there. But thanks everybody for attending, and a copy of the presentation will be sent out tomorrow.
Thanks everyone. Have a good day.